Okay, so let's get started. In the previous class, we were discussing how to derive the capacity region of the two-user discrete memoryless multiple access channel. And in the last class, we saw an achievability proof. In particular, we saw that the following rate region is achievable. So the rate region is given by the convex closure of all of these pentagons. So take the union of all possible pentagons, where each pentagon is described by the following inequalities on the rate. And you take the convex closure of all of these rate pairs, or you take the convex closure of all of these, take the union and then the convex closure of the union of all of these pentagons. That gives you the capacity region, right? So let's, in this class, we'll see the converse proof and some discussion regarding the achievability proof. So the achievability proof, we used what I called successive interference cancellation, or another way to put it is sequential decoding of the code words. Right? You first decoded the first code word, and that is the code word corresponding to user 1, and then used that estimate as one of the inputs to the channel, and assuming that this was the input, you try to decode code word 2. Right? So the question is, of course, it is optimal in the sense that it is sufficient. So successive interference cancellation as well as time sharing is sufficient to achieve the entire rate region or the entire capacity region. Right? But on the other hand, it is not optimal in terms of the probability of error. So let's look at one of these pentagons. Right? So let's look at one such pentagon. Say this is R1, this is R2, this is I of x2, y given x1, this is I of x1, y given x2, right? And this line corresponds to the rate pair R1 plus R2 equal to I of x1, x2, y. Right? And the way we showed proved achievability was that you prove that the corner points are achievable. In particular, we showed that this corner point is achievable, and using a very similar argument, you can show that this corner point is also achievable. Now, in order to achieve any rate pair which is not a corner point, maybe some point along this line, you would use time sharing. Right? So suppose that so any point over here, let's look at this particular point, this blue point, R1, R2. So let's call this point R1 prime, R2 prime, and this point R1 double prime, R2 double prime. So since R1 comma R2 lies in the line joining these 2 points, it can obviously be written as a convex combination of the 2 points. So you can write all R1 to be equal to alpha R1 prime plus 1 minus alpha R1 double prime, and R2 can be written as alpha R2 prime plus 1 minus alpha R2 double prime. Right? And so which means that if you want to show that this pair is achievable, if you want to design a code for to achieve this particular rate pair, then what would you do? Anyone? So I know that I can construct encoders and decoders which let me achieve R1 prime, R2 prime, and there also exist encoders which achieve R1 double prime and R2 double prime. Now if I want to achieve R1 comma R2, what would I do?
We can
So time
cascade them.
sharing, as you said previously.
Yes. So can you elaborate on that? What would be done?
So given a fraction of time, alpha part
Okay.
of the time slot will be given to R1, that is user 1, and the left power will, left time, that is 1 minus alpha of the time will be given to the second user.
So that would be TDMA, right? It would not exactly be time sharing. Right, so it's close, but
Similar, right? So then,
correct. So corresponding to R1 prime, R2 prime, you would have some particular encoder and decoder, right? So let's call this encoder prime, decoder prime. So for every n, there is an encoder prime and decoder prime. And similarly, corresponding to this particular rate pair, there is some other set of encoders and decoders. Right? So what would you do for alpha n channel uses? Use encoder prime for alpha n channel uses and decoder prime for alpha n channel uses. Right? So for the remaining 1 minus alpha n channel uses, so for the remaining 1 minus alpha fraction of the time, you would use the second set of encoders and decoders. Right? But of course, so each of these is a sequence of encoders and decoders. So you use this for alpha n channel uses, and you use this for 1 minus alpha n channel uses. So in particular, the message for each user, user 1, user 2, so you have a total of kn or nr1 message bits. NR2 user 2 has NR2 message bits. So these are split into two parts, right? So one which is alpha R1 prime bits, and the remaining 1 minus alpha R2 prime bits, sorry, R1 double prime bits. Similarly, user 2 splits its message, which consists of NR2 bits, into two parts. One which consists of NR2 prime bits, sorry, alpha NR2 prime bits, and the remaining would be 1 minus alpha NR2 double prime bits. Right? So it's just the so message is just the sequence of bits. You split it into two parts, right? And the first part of the message is encoded using the first encoder. Right? So you get a code word of length alpha times n. Similarly, user 2 does the same thing. It encodes the first alpha n bits using encoder prime. So you get a code word of length alpha n bits, and the rest of the message bits are encoded using the second scheme. right? So to give the second part of the code word, which is of length 1 minus alpha n. Right, and these are transmitted across the channel. The receiver also decodes in a similar fashion. It gets a combination of these two. So you transmit this across the channel, and then the receiver gets to see a yn. The first alpha n channel uses consists, so for the first alpha n channel uses, this is affected by the first code word of user 1 and user 2. And for the remaining 1 minus alpha n channel uses, the received sequence depends on the red code words, which are encoded using the second scheme. Right, and then the receiver uses decoder prime to recover the first parts of the two messages. And then for the second half, or for the second fraction, 1 minus alpha fraction, it uses decoder double prime. Right? So each of these gives you two separate parts of the message, and then you concatenate the two to get the overall message, the overall estimate of the message. All right. So this much is clear.
Yes, sir.
Sir, a small doubt.
Yes.
As per like we have a previous, is time division multiplexing and time sharing same? And you're in TDMA you're saying that time division will be there, but it will be same encoder and decoder. Is it right? I'm a
No,
bit
so
confused in
yes,
this.
so there's a subtle difference between time division multiplexing and time sharing. So
Okay.
time division multiplexing is a very specific case of time sharing. So TDMA is a special case time sharing. So you can use time sharing for any pair of schemes, right? So you have one set of encoders and decoders. In time sharing, for alpha fraction of the time, you use the first scheme, the first encoder decoder for both users. So both users could simultaneously transmit, but they use a different set of encoders and decoders for the first alpha n channel users, and for the remaining 1 minus alpha n channel users, they use another set of encoders and decoders, right? But this is more general because both could transmit in all channel users. TDMA is a specific case where in one set of channel users, only one user is active. So all the other users remain silent. Right? So this is one specific instance of time sharing, which is one particular scheme where for maybe alpha n channel users, one user talks, whereas the other remains silent. And for the remaining alpha n channel users, the second user talks while the first user remains silent. Whereas in time sharing, it's much more general. So both users could talk in the first alpha n channel users, but they use one particular set of encoders and decoders. And for the remaining one alpha n channel users, again, both users could simultaneously talk, but they use a different set of encoders and decoders. Right?
Yes, yes. I think the term, the time sharing term itself, I felt misleading. If I'm
Yes.
not.
So that is why. So time division multiple access. So that's generally an orthogonal multiple access scheme.
Uh,
Wherein you're allocating orthogonal resources, in this case time, whereas time sharing is much more general, so it does not necessarily correspond to an orthogonal multiple access scheme. Everyone could talk at the same time, so
yes.
everyone is sharing the same resources.
Sir, this is Girish. Sir, I'm having one more doubt.
Yes, Girish.
Sir, am I audible, sir?
Yes, there seemed to be a little bit of noise in the middle, but now it's fine.
So, sir, I was just asking,
Uh-huh.
so will there be any kind of synchronization kind of thing with respect to these encoders and decoders?
So we're always assuming that on both all systems are completely synchronized, and that is taken care of separately. Right? So you know exactly when each symbol is transmitted. Both users transmit symbols simultaneously, and the receiver knows exactly when a particular symbol is received. So the underlying assumption is that there is maybe a common clock for all of these users, and those clocks are or there are multiple clocks which are perfectly synchronized.
Sir, what I mean, what's like my understanding of synchronization, or what I want to ask is like,
Mhm.
basically, if let's suppose user one is transmitting, where
Yes.
he forms a part of alpha and users,
Okay.
and then he is transmitting using encoder one.
Okay.
And when it comes to the decoding part,
Okay.
let's suppose if that particular decoder is not exactly, like, this decoder is not an dedicated kind of decoder for this particular user. It might
Uh,
be a general decoder with respect to both the users, right? As many users as in.
I'm not. So I mean, there are of course different ways to model this. So one thing is that a so okay. So the assumption here is that the encoder. So all users know which encoder is being used at a given point in time. All right.
Okay.
Sorry, there's a lot of noise from your end.
Sir, please excuse me. Like, there is a particular function which is going somewhere surrounding me, so I can't help it.
Sorry, you're not audible at all.
Sir, I was just telling that some other function is actually going from
Okay, sure,
fireworks are
sure.
going on, so I can't help it.
Okay, so maybe can you just mute yourself when not speaking? That might make it a little easier. Yeah, thanks. You can just unmute yourself when you want to ask, right? So one general assumption that we make in this entire course is that the encoder and decoder is known to all. So at any point in time, if you say that user one is going to use a particular encoder or a particular codebook, and user two is going to use one particular encoder and one particular codebook, everyone knows which encoder is being used, which codebook is being used, and so on. And the second assumption is that the channel is known perfectly by all users. Right. So as you mentioned, so there could be different such synchronization issues. One is, of course, when the exact encoder and when the decoder doesn't know exactly which encoder is being used by, say, user one or user two. Right? Or you want, as you mentioned, you want to use a generic decoder which works for a particular class of encoders. And one such decoder is, for example, the maximum likelihood or the closest point decoder, right? The minimum distance decoder. But of course, this of course requires you to know what is the code book which is used, right? Because otherwise, there is really no way to decode. Now there's a separate line of work which deals with all of these imperfections. Right? So one imperfection is when you don't know the channel exactly. So for example, you could know that it's maybe a fading channel, but you don't know the exact distribution of the fading coefficients, or maybe the additive noise is not exactly Gaussian. Right? In which case, things become a lot more complicated. But again, you can derive formal results in terms of the mismatch between the uh, between the actual channel and the decoder being used. So you tailor your decoder for a particular channel, but the actual decoder, the actual channel could be slightly different from the channel for which you have designed the encoder and decoder for. And this generally comes under the class of problems called say decoding, mismatched decoding. But a lot of things are still not known. Even the point-to-point case, things are kind of well understood, but it's not a completely solved problem. Then of course
Right.
there is, yes please.
Yeah, I was just asking that, like, so when let's suppose 1 minus alpha user, like one particular user in that particular group is actually transmitting, then there may be a mismatch when it is actually decoding using this decoder prime, right? Sir? So there
So
such kind of mismatches may occur.
mismatch due to what?
Like, sir, like if it is like, unless otherwise we know, okay, it is encoder double prime, then only it use the decoder double prime to decode. That is what
Correct.
the final state, right?
That is true. But this information we assume is already shared. It's decided beforehand, and typically, if you, for example, if you look at a standard wireless communication system, you have a lot of these additional channels or additional lines of communication between the cell phones and the base station. There are these control channels and synchronization channels, which wherein you have these little bits of information exchanging, which tell both users, or they decide beforehand which encoder is to be used, which decoder is to be used, and so on. Right. So, but that is an additional very small overhead, and that doesn't really affect the rate significantly. Right? So there's typically a preset collection of encoders and decoders. You decide that if a certain condition happens, if your channel is such and such, and if your rate is such and such, then you use this particular encoder and this particular decoder. And there are, between the transmitter and the receiver, generally there are parallel channels, like these control and synchronization channels, wherein maybe a base station tells the mobile users, okay, you are supposed to use this particular encoder for this much of time, and this particular decoder for this much of time. That's how things are practically implemented, but that doesn't significantly affect things. Yes.
Thank you.
Okay. All right. Yes. So since we're using a different set of encoders and decoders for alpha n channel uses and the remaining 1 minus alpha n channel uses, let's for now let's assume that alpha is less than half. Okay. So the probability of error, as we've seen, is the overall probability of error is sort of decays exponentially in the block length. Right? And the probability that an error occurs is basically the sum of the probabilities of errors of the first part plus the second part. So if the first part of the message is decoded incorrectly, then you make an error. If the second part is decoded incorrectly, also it becomes an error. Right? So if either part is decoded incorrectly, it's an error. So the probability of error is actually very close to the probability of error for the first block plus the probability of error of decoding the second block, which is of n minus 1 minus alpha n channel uses. And this, of course, you get using the union bound, but this, since the two blocks are independent, this is much more close. Sorry. But as we've seen, the probability of error of decoding the first block is decaying exponentially in some. So this is some alpha, or maybe let me call it beta 1 times n. And the second probability of error, it's n alpha times beta 1, where this beta 1 depends only on the rates and probably the channel. The probability of error for decoding the second block is e to the minus beta 1 minus alpha n. Right? Since alpha is less than half, typically this particular term dominates the probability of error. Right? So the overall probability of error is decays exponentially, but it decays exponentially in alpha n, assuming that alpha is less than half. If it's greater than half, then the dominant term is an exponentially decaying term in 1 minus alpha n. Right? On the other hand, if we try to do joint decoding, if we try to design a joint decoder, then we can design a scheme which achieves the same rate pair, but the probability of error is now not is not decaying in alpha n, but in fact directly decays as e to the minus some constant times n. So if you do joint decoding, you can achieve the same rate just as you did for successive something like using successive cancellation decoding, but you can achieve a much lower probability of error. Right? And that is typically why in many scenarios people go for joint decoding over successive interference cancellation decoding. However, in many cases, something like successive interference cancellation, it generally has much lower decoding complexity. Although you pay the price in terms of the probability of error, you gain in terms of complexity of decoding. Now, the successive interference cancellation decoder is good for multiple access channels, in the sense that it achieves the entire capacity region. But if you look at more complicated channels or other multi-user channels such as the broadcast channel or even the interference channel, this successive interference cancellation is in general not optimal. It does not achieve the entire rate region. You do have to do joint decoding. But that's the speciality of multiple access channel. It is much simpler, and of course it has been completely solved. We know exactly what the capacity region is, and there are also simple enough schemes that let you achieve any rate pair in or any rate point in the capacity region. Right. So in that sense, the multiple access channel is kind of solved. But that is not the case for broadcast channels or even the interference channel. All right. Any questions up to this point? All right. So now that we've seen the achievability result, let's try to prove a converse. So what we want to show is that every rate pair which is achievable, that is, if we have an R1, R2, then if it's achievable, it means that we can construct encoders and decoders, two encoders, one for each user, and one decoder for the receiver, for which operate at rates R1 and R2 respectively. And at the same time, the probability of decoding error decays with n. Right? As n tends to infinity, we can make the probability of error arbitrarily small. right? So if a particular rate pair is achievable, then it must necessarily satisfy these conditions. So if any one of these conditions is not satisfied, then it means that it's not possible to construct an encoder not possible to construct encoders and decoders for which the probability of error vanishes with it, right? So the claim is that it must satisfy these conditions, and this condition looks a little bit different from what we've seen before. So this condition, so it consists of three conditions. One, that R1 is less than or equal to the mutual information between x1, y given x2 and q. Similarly, R2 is less than or equal to the mutual information between x2, y given x1, q. And R1 plus R2 is less than or equal to the mutual information between x1, x2, and y conditioned on q. But this q is what I call a time-sharing random variable. So these conditions must necessarily be satisfied for some joint distribution on x1, x2, y, and q, which follow the following properties. So py given x1, x2 is of course determined by the channel. So the freedom is in choosing x1 and x2, but they can be chosen in the following manner. So q, so you generate a random q, which comes from any alphabet which is finite valued. There's no real constraint on the cardinality of q, but conditioned on q, x1 and x2 are independent of each other. So they're conditionally independent given q, and then you pass x1, x2 through the channel at y. So in some sense, q, x1, x2, and y form a Markov chain, right? So every rate pair which is achievable must necessarily satisfy this. Right? And the claim is that this essentially corresponds to the same region which was described over here. The same rate region which was described over here. So remember that this rate region was sort of a union or a convex, a set of all convex combinations of pentagons, right? And my claim is that this particular rate region that I described just now, this is also a convex combination of pentagons, right? And how do you see this? Now, it's easy to see because for a particular realization of Q, for Q equal to some particular realization of Q, this particular thing essentially corresponds to R1 less than or equal to mutual information between x1, y given x2 equal to Q, R2 less than or equal to the mutual information between x2, y given x1, and Q equal to Q, and R1 plus R2 is less than or equal to the mutual information between x1, x2, and y given Q equal to little q. So if you fix a particular realization of Q, essentially what you get two PMFs, Px1 given Q equal to little q, Px2 given Q equal to little q. Right? And these result in some particular y. So for each Q equal to little q, this region corresponds to a pentagon. Right? And this particular rate region for any distribution on Q, this corresponds to a convex combination of pentagons. So this essentially corresponds to so for any PQ, this corresponds to this is a convex combination of pentagons. All right. So for every distribution, this corresponds to a convex combination. So therefore, if you look at the first region, or the region that is the capacity region which we showed is achievable, the rate region which is achievable, that every point in that rate region can be described using these inequalities. So you choose a suitable PQ, and that gives you any rate point. Right? Any rate point there is also a rate point here. And similarly, if you look at any R1, R2 which satisfies these conditions, this is, of course, it is obtained by some convex combination of points within pentagons. So therefore, if it belongs to this rate region, it also belongs to this particular rate region. Right? So sorry, if it belongs to this particular rate region, it also belongs to that achievable rate region. So in some sense, these two are the two descriptions are the same. They're both describing the same rate region. Right? Is that clear? Does it make sense? So in the achievability part, we showed that some particular region is achievable. So every point in some region is achievable. For the converse, we're going to show the same, but the way we describe this rate region is slightly different. Earlier, we showed that any point within a pentagon is achievable, and therefore any point in the convex combination of pentagons is also achievable just by the time sharing argument. Right? And for every PQ, this rate region is basically just a convex combination of pentagons, and therefore the two rate regions, one which is described over here and one which was described in the achievability part, all the two are essentially equivalent regions. So they're two equivalent descriptions of the same region. All right. Any questions? So in general, in information theory, these variables, such as this Q, so note that x1 and x2 are x1, x2, and y are in some sense specified by the problem. Right? So x1 and x2 are the inputs to the channel, input by user 1, x2 is the input by user 2, and y is the output of the channel, and that the conditional distribution is specified. Right? But when we describe the achievable rate region, we have this new term which is a Q, which we're introducing. So it's sometimes called a time sharing random variable. It is also in the information theory literature called an auxiliary random variable. So it's an auxiliary random variable, and it is just a convenient description of the capacity region. Because it lets us describe convex combinations of rate pairs, right? Which you could otherwise not do. So when I described the achievable rate region, I said that it's a convex combination of pentagons, and there is no neat way of writing it in terms of inequalities, right? It's a complicated union of many pentagons, and that is a more complicated way of describing a rate region. But this By introducing this auxiliary random variable, I can simply state it in terms of three inequalities. I don't have to say that it's a union of many things. So as long as R1, R2 satisfy this for some particular joint distribution satisfying according to PQ, Px1 given Q, Px2 given Q, this region is achievable and it's both necessary and sufficient. So every rate pair must satisfy this for some joint distribution PQ, Px1 given Q, Px2 given Q. And at the same time, any rate pair satisfying these three conditions for some joint distribution PQ x1, x2, we can construct encoders and decoders with vanishingly small probability of error. Okay, so this, as I mentioned, is this by introducing this auxiliary random variable, you get a more convenient description of the set of all achievable rate pairs. And why is this important? Now, suppose that someone gives you a channel, someone gives you a multiple access channel, and you just want to know whether it is possible to operate at some particular rate. Okay, so is it possible? So someone gives you a py given x1, x2, right? And as a system designer, even before designing a code, someone asks you, is it possible to operate at rate pairs R1, R2, right? So even before designing encoders and decoders, you want to know if it is possible to operate, right? And how do you do that? So the only way you can, so if you had the first description, then you would need to find pentagons and then find out whether the point is in the union of some particular pentagon or not, right? Or in the convex combination of different pentagons or not. But on the other hand, this description is much more convenient because all I now need to do is find a PQ, Px1 given Q and Px2 given Q, such that I can express R1, R2 as one satisfying these three inequalities, right? So it's easier to check whether a particular rate pair is this description. With this description, it is easier to check whether a particular rate pair is achievable or not. Right? So that's what the auxiliary random variables enable us to do. Now, this is not a very convenient form because, at least at this point, I'm saying that Q is finite valued. Right? The size of Q could be very, very large. So the space of distributions over which you need to check these inequalities could be very, very huge, because the larger the size of your alphabet, the larger the search space for PQ, Px1 given Q and Px2 given Q. All right, but later on we'll see that this is not the case. You can use a smaller alphabet for Q. So that is, it's not a trivial statement. It does require a complicated proof. But in fact, the size, so you don't need to look at distributions over all possible Q. You can just look at distributions over binary value Q. All right. So using these approaches, by knowing that Q, the size of Q is suitably small. So to find out whether a particular R1 and R2 are achievable, you just search over all possible distributions, PQ, Px1 given Q, Px2 given Q, and then in this search space, find out whether R1, R2 satisfies these inequalities. Right? Even if you can find one set of distributions for which these inequalities are satisfied, then you know that it is possible to construct encoders and decoders to operate at that particular rate pair. If it is not possible to find, or if you don't find a distribution for which these are satisfied, then it means that that particular R1 and R2 are not achievable, right? Any questions? Right. So it's important to note that at this point. So in point-to-point information theory, you could to check whether a particular rate is achievable, you just have to compute a mutual information. So or in other words, compute the capacity, which is just the maximum of the mutual information, and that is relatively easier, right? You have a concave, the mutual information is a concave function of the input of px. So all you need to do is maximize the mutual information. You get a number. If you, so any rate below this particular number is achievable. That's easy to compute. But as soon as you go to multi-user channels, even verifying whether a particular rate pair is achievable or not is not an easy task, right? Because now your search space, so it is not enough to just compute one number. So the set of achievable rate pairs forms some region, some convex region. And you need to verify whether a particular R1, R2 lies in that region or not. But fortunately, the search space is not too large. So you can find a queue which is of suitable small size, and then you look at all these possible distributions and find whether these conditions are satisfied for some joint distribution. All right. Okay. So now let's look at the proof of the converse. Right? So in the interest of time, I won't do this in detail because this is again a very, it's the same approach as what we did for the point-to-point case, and so I'll also need your help in filling up some of the steps. Right? So in any converse proof, so every converse proof basically makes use of 2 or 3 different steps. One step is, of course, Fanos inequality. So whenever you have a h of message given the received signal or received sequence, you know that you should be able to decode the message reliably given the received sequence. So therefore, you can always use Fanos inequality to upper bound this as h of pe plus pe log the size of x, or in other words, h of pe plus the probability of error times n times the rate, right? Which, since we want the probability of error to be vanishingly small, this is at most some n times epsilon. All right, so that is one key point, one key tool that we will use in any converse proof. Right, so the first step is always to start with n times the rate that you're interested in, and somehow bring in a term which involves the entropy of the message given the received sequence. Right. So we have n times R1 plus R2, which is just equal to the joint entropy of the two messages M1 and M2. Right? So the messages are independent of each other and are uniformly distributed. Therefore, the entropy of M1, M2 is equal to n times R1 plus n times R2. Okay. So now we have this, and we want to bring in the received signal. Right. So the first step to do is h of M1, M2 I will just add and subtract h of m1, m2 given yn to this term, given yn. All right. So what is this term equal to? So it's h of m1, m2 minus h of m1, m2 given yn.
Mutual information.
Correct. So it's the mutual information between m1, m2 and yn. Right? Plus, now I have h of m1, m2 given yn. And I know that given yn, if a particular rate pair is achievable, then I should be able to reliably decode m1 and m2. So now I can use Fano's inequality, right, and say that this is at most n times some epsilon, right? Okay, so now I have this, and the next step in any converse proof is now I have I of m1, m2, the mutual information between a message and yn. I want to, this is more complicated because I don't know how this will behave. Instead, I want a mutual information between the input to the channel and the output to the channel, right? So can I do that, and how would I do it? I somehow want I of x1n, x2n, and yn. Right? Can I do this, and how would I do it?
Data processing inequality.
Yes. Very good. So we know that m1, m2, x1, x2, and yn, they form a Markov chain, right? Because given x1 and x2, yn is independent of the messages, and x1 and x2 are basically the encodings of m1 and m2, right? So you just use data processing. We use data processing inequality. Okay. So now the rate is always going to be less than or equal to some complicated mutual information term. So it's an n letter mutual information term plus n times epsilon, right? And now this could depend on joint distributions on x1n and x2n. Right? So the claim is to show that this is less than or equal to a sum of mutual informations of the individual terms, right? So how do you do that? So this is equal to, so let me write this as h of yn minus h of yn given x1n, x2n plus n times epsilon, right? So this is equal to summation I equal to 1 to n h of yi given yi minus 1 minus h of yi given yi minus 1 x1n, x2n plus n epsilon. So basically here I've just used the chain rule for entropy, right? Okay. So now basically what I want to do at this point is I want to write this in terms of h of yi minus h of yi given x1 of I, x2 of I. Okay? Because that will get me to a form where I can, because I want to bring it to this particular form. So I want to show that this inequality has to be satisfied. Right? So from this, what I call multi-letter expression for the mutual information, I want to get a single letter expression for the mutual information. I don't want it to depend on n in any form. Okay? So let's look at the first term. Can I say something about h of yi given yi minus 1? Do I have any relationship with just h of yi? Anyone? Can I say that h of yi given yi minus 1 is less than or equal to h of yi?
Yes, sir. So
Conditioning
conditioning.
reduces.
Yes, exactly. So conditioning reduces entropy, and therefore h of, so this term is less than or equal to this term. So that's fine. So the first set of terms is now taken care of. Now the second term. So I want, again, as I mentioned, I want to write this as a sum of mutual informations, right? So I basically want this term, h of yi given x1 of I, x2 of I, right? Can I make this statement somehow? So obviously I can't use an upper bound for this, right? I can't use the fact that conditioning reduces entropy
Negative.
because I have the negative sign. So my claim is that this quantity is equal to this quantity. Can someone tell me why?
Independent because
Exactly. So it's a memoryless channel, right?
Yes, yes.
So it's a memoryless channel. So given the inputs at the ith time instant, the output at the ith time instant is independent of everything else. So basically, we're just using the memoryless property here. Right? And therefore, we have this particular form. So it is the summation overall I going from 1 through n of the mutual information between x1i, y1, sorry, x1i, x2i, and yi plus some n times epsilon. Right? So this is a key step. So note that in any converse proof, these are generally the main steps that you will use. You'll use Fanos inequality to get rid of some of those conditional entropy terms, and then you typically use the data processing inequality to so that instead of mutual information between a message and the received signal, you have mutual information between input of the channel and output of the channel. And then you need to somehow massage this so that you get a sum of mutual informations in some fashion, right? Now, for the point-to-point channel, we could just say that, okay, this is always less than or equal to the capacity, so we are done, right? But that is not the case over here, because there is no maximization of mutual information, right? And we want something better than just max over all of this, right? We can obviously say that this sum is less than or equal to n times the maximum of this mutual information, but there is something that we don't want to do. We want to get a better bound than that. All right, and in fact, that is what we will do. So R1 plus R2 is therefore less than or equal to 1 by n times the summation I going from 1 through n of the mutual information between x1 of I, x2 of I, and yi, plus some epsilon, which that epsilon can be conveniently ignored, right? So we have this particular form, but what we actually want is something in this form, right? So it's a mutual information between x1, x2, and y given q, right? And the way to get this is the following. So this quantity, for each I, we have a particular px1, x2, y. All right, so we have one for each particular I. Correct? And what is this? This is basically a convex combination. So 1 over n times the sum of the mutual informations is basically a convex combination of the mutual informations, right? Because you're scaling by 1 over n. It's an equal convex combinations, right? So essentially, you can write this. You can write this as the mutual information between x1, x2, and y given q plus epsilon. So basically, this term is equal to this. So maybe let's just see a quick example to see why that is the case. Okay, let's just look at two terms. So n equal to 2, right? So we have half the mutual information between x1, 1, x2, 1, y1, plus half mutual information between x1, 2, x2, 2, and y1. Right? So this is basically the term over here, and I want to write this in terms of this mutual information involving a time sharing random variable, and the way to do it is just simple. So you look at q to be either 1 or 2, right? So when q equal to 1, then p x1, x2, y given q equal to 1 essentially corresponds to this PMF, the PMF which gives you this. So it is py given x1, x2, which is specified by the channel, times p x1 of 1, p x2, 1, which gives you this, the distribution which gives you this mutual information term. And similarly, p x1, x2, y given q equal to 2 is basically p y given x1, x2 of times px1, 2, px2, 2. So it's basically the distribution which gives you this particular term. So if you take the uniform distribution on Q, then basically what you get is this, right? So the mutual information between x1, x2, and y given q is basically half or half I of x1, x2, y given q equal to 1 plus half the mutual information between x1, x2, and y given q equal to 2. Correct? And that is essentially what we have done over here. Right? So we had an n letter term, and we're just writing it, we're just representing it using a particular time sharing random variable. Right? And q is anyway finite because the size of q can be at most n. Right? So for every n, this needs to be satisfied. So effectively, R1 plus R2 should be less than or equal to this particular mutual information for some particular distribution on Q, and for conditional PMFs, Px1 given Q and Px2 given Q. Right? Any questions? Right. So this is just another way. Again, all that you need to keep in mind is that it is just another way of representing 1 over n times the summation of the mutual informations in terms of a conditional mutual information, where this condition is taken over some time sharing random variable. And right now at the moment, all q has to be is finite valued. There is no necessary bound on the cardinality of q. But in fact, you can show that this rate region can be equivalently represented in terms of a rate region where q is bounded. It is not arbitrarily large. It's in fact very, very small. All right. So another thing to keep in mind in general is that whenever you have any complicated channel coding problem, so for example, it could be a fading channel or more particularly channels with memory, like a channel where you have frequency selective fading or any other dependence between the consecutive symbols which are transmitted across the channel, where the where basically memorylessness property is not satisfied. Right? So in that case, generally speaking, you cannot obtain a closed form expression of this form. Right? So you cannot write that the rate is less than or equal to a sum of mutual informations, because note that both the first step and the second step, both Fanos inequality and the data processing inequality, hold for any joint distribution. It doesn't really matter what the channel behavior is, right? But in going from this step to this step, we crucially use the property that the channel is memoryless. Right? So whenever you're trying to, even let's say in your research, whenever you're trying to derive rate bounds, and you think that the capacity or the achievable rate can be given in terms of some mutual information term, you have to be careful. If the channel is memoryless, then generally speaking, this will hold. You can represent the achievable rate or the capacity in terms of some mutual information. But on the other hand, if the channel is not memoryless, then generally speaking, this does not hold. You cannot, in most cases, you do not have a simple mutual information term. Right? So, and that's very important to keep in mind. All right. So we've seen a bound on the sum rate. Now, similarly, using using an almost identical approach, you can derive bounds on the individual rates. You can show that NR1 is less than or equal to the sum of mutual informations between x1 y given x2. So essentially you will get that this is I of x1 y given x2 and q, where q is a time sharing random variable, plus, so r1 is less than or equal to this plus epsilon. All right, and again, I won't go through the steps because it's just going to be repetitive. So as an exercise, I want you to just make sure, go through all of these steps and try to justify each step of the proof, right? So try to identify how you go from one step to the other, why there is an equality, why there is an inequality, and how each of these equalities and inequalities are justified, right? And that lets you understand and also practice using the basic information theory results like data processing inequality, Fanos inequality, and so on. Right? Because once you get a grasp of these tools, you can apply it to any sort of information theory problem. All right. Any questions? Okay, so if not, then let's stop at this point. We'll continue in the next class.